Welcome to the 6th lecture on solid state structures. We said bring the ions together and they try and pack around each other as best they can. But actually that sort of is asking a question. How do you get the ions in the first place? The obvious way you get the ions, of course, is that somebody has to lose electrons and somebody has to gain electrons. And both of those processes involve energy changes. So what kind of energy are we talking about here? If we simply combine sodium with chlorine, the sodium becomes a cation, the chlorine becomes an anion, we end up with sodium chloride. The energy required to remove 1 mole of electrons from 1 mole of sodium, its ionization energy, is plus 496 kilojoules per mole. The energy released from chlorine when 1 mole of electrons is added to 1 mole of chlorine atoms, its electron affinity, is minus 348 kilojoules per mole. So if that was the only thing that happened, that is, we simply removed a mole of electrons from a mole of sodium atoms and gave them to a mole of chlorine atoms, then the whole process would be endothermic by about 150 kilojoules per mole, which basically means it wouldn't happen. Endothermic reactions tend to be very unfavorable, and highly endothermic reactions tend never to happen. Yet, this reaction is not endothermic. In fact, not only is it spontaneous, it is considerably exothermic in process. A lot of energy is released in this reaction. So where is it coming from? Since it's not coming from just transferring the electrons. In fact, if you simply mix sodium vapor, that is gas, with chlorine gas, in the gas phase, you do in fact not form sodium chloride. The electron does not transfer, because in fact that process would be endothermic. But that's not what's happening. You're combining the sodium and the chlorine and getting solid sodium chloride. The ions are combining. And it is combining the ions that is where all this energy is coming from, because they follow Coulomb's law. The energy of two charges as they come together depends on the amount of the charge, Q1 and Q2, and how close they are together. If you're bringing like charges together, that is cations and cations or anions and anions, then as you bring them together, the energy increases. You have to force them together. The like ions do not attract each other. On the other hand, if the charges are opposite, one positive and one negative, then the energy is lowered as you bring them together, and the closer you bring them together, the lower the energy becomes. So taking the sodium ions and chloride ions and bringing them together to form a solid, that is a lattice, does in fact have a considerably exothermic process. And we talk about the lattice energy of the solid, the energy brought about that's released by bringing the opposite ions together into their 3D array. So how much lattice energy are we talking about? Well, unfortunately, we can't get the lattice energy directly from the reaction. That is, we can't create a mole of sodium ions and a mole of chlorine ions in the gas phase and bring them together and measure the change in energy. So we can't actually do that process. So what are we going to do instead? What we're going to do instead is make use of what is known as Hess's law. The law of Hess simply says that the total energy change of a reaction is the same regardless of how the reaction is run. This is basically a variation of the first law of thermodynamics that says the energy change of the universe is zero. If you could run a reaction in two different ways and get different amounts of energy out, it would therefore be possible to create energy by running the reaction one way to begin with and then running it the other way in reverse, and you'd end up where you started, but you'd have more energy than you had to start with, which is clearly impossible. So any way you run the reaction, whether you do it all at once, you do it slowly in steps, or in any other convoluted fashion, it doesn't matter. The total energy you get out is the same. And so, If we simply throw the sodium into the chlorine, we get out 411 kilojoules per mole. So now let's run the reaction in a little more complicated fashion. Let's break it down into separate steps. Well, the first thing we're going to have to do is get the atoms apart. To begin with, the chlorine is in the gas phase already, but it's in the form of molecules. So the first thing we're going to have to do is get the chlorine molecules apart. The bond energy of a mole of chlorine is 244 kilojoules per mole. And since we have half a mole of chlorines, we're going to need half that amount of energy. Or in other words, 122 kilojoules of energy. The sodium's a solid. We are going to have to get it into the gas phase. So we need the heat of sublimation for 1 mole of sodium, which is plus 108 kilojoules per mole. So finally we have the isolated atoms, and now we can transfer the electrons. First we have to pull the electrons off the sodium. We said the ionization energy for sodium is 496 kilojoules per mole. Now we can transfer that mole of electrons to our mole of chlorine atoms. And that's the electron affinity for chlorine, which is minus 348 kilojoules per mole. And so now we have our sodium ions and chloride ions in the gas phase. We can bring them together to form the lattice and get out the lattice energy. But like we said, we can't actually measure that. But Hess's law says if you start on the bottom left and end up on the bottom right, it doesn't matter how you get there. So doing it in one step, throwing the sodium into the chlorine, gets us out minus 411 kilojoules per mole. And doing it the long convoluted in several steps has to total out to that same minus 411 kilojoules per mole. So it's plus 122 plus 108 plus 496 plus minus 348 plus whatever the lattice energy is. And so we can calculate the lattice energy for the sodium chloride is minus 789 kilojoules per mole. That is, the formation of the lattice is a conspicuously exothermic process. And so this is what is actually necessary to have the energy to create the ions. If we're just transferring the electrons, it's not happening. But we're transferring the electrons and creating the ionic lattice. And that is where our energy comes out. And so what kind of lattices do we actually get from our ions when we bring them together? We've already noticed in the case where the ions are approximately the same size, we get the cesium chloride structure, with one of the ions in the center surrounded by 8 of the other ions. With the smaller ions fitting into the octahedral holes of a close-packed array of anions, we get what is known as a sodium chloride structure. In this case, the yellow represent the chlorides, and they're simply, as you can see, in a face-centered cube. Meanwhile, the sodiums in this case occupy all the octahedral holes that are created by the triangles of chlorides that sit next to each other in the array. If we're going to get the stoichiometry right for a 1-to-1 ion, where the smaller ion ends up in the tetrahedral holes, we're going to get this kind of arrangement. The larger ion, again, still forms a face-centered cube, and the smaller ion occupies the tetrahedral holes. It's just that it occupies every other tetrahedral hole. So there are only 4 yellow ones for each of the blue ones in that structure. And that's known as a zinc sulfide structure. And if the small ion is so small it can't even manage to fill up the tetrahedral hole, then we get this. This is known as a rutile structure. And you'll notice that each of the white ions is in the center of a triangle of blue ions. Meanwhile, the blue ions are surrounded by 6, and they are occupying the octahedral hole in the arrangement of the white ions. And that's known as a rutile structure. Which brings us to the end of today's lecture on ionic crystal structures. Have a nice day.